Welcome! Our project sets out to recreate a true classic, the 1978 Space Invaders arcade game, with complete fidelity to the original hardware. We're building an emulator that can load and execute the original ROM byte for byte on an Intel 8080 CPU with accurate memory and I/O behavior. But what makes this project unique is how we built it. Every line of code, every design choice, was created with the help of AI development partners like ChatGPT, DeepSeek, Claude.ai, and GitHub Copilot through careful prompt engineering. Every exchange was logged, analyzed, and iteratively improved. This is also a project about bridging eras. We brought together retro computing, reverse engineering, and low-level systems programming with modern tooling like generative AI to explore the potential of human-AI teams tackling complex, accuracy-critical software. This emulator gave us hands-on exposure to systems-level programming. We had to understand and simulate the Intel 8080 CPU architecture, implement hardware-accurate memory mapping, and reproduce I/O behavior that interfaces directly with the original ROM. This kind of context where AI tools must be guided very precisely, which made it an ideal testbed for studying AI-assisted development. One of our key goals was to explore the practical capabilities of AI coding assistance in real-world systems programming. Each model brought strengths and limitations, and we experimented with prompt structure, context windows, and iterative refinement to produce quality output. What made this interesting was that no single prompt or model could solve everything. We had to treat the AI like a junior engineer, asking the right questions, checking the output thoroughly, and correcting or rejecting mistakes. Through this process, we discovered real and measurable benefits to AI-assisted development, even in low-level technical domains. First, it accelerated prototyping. We could get test scaffolds, boilerplate, or even a first draft of a disassembler or CPU instruction table quickly. AI models can fill in the blanks on legacy specs, explain unfamiliar instructions, or walk through architectural behavior on demand. Code from LLMs tended to follow consistent modular structures. AI code also saved time on documentation and testing, generating helpful comments and unit test templates. Now, we will show a brief demo of the project in action. Hello everyone, for my part of the project, I led the design and implementation of the emulator's memory and I/O systems. This included mapping memory regions, handling hardware-level protections, and simulating I/O ports and timing critical hardware behavior, like shift registers and sound output. The first steps were implementing the full 64 kilobytes memory map, including ROM, video RAM, and work RAM. I enforced read-only and read-write protections and added utilities to translate, debug, and validate memory access. Then, I managed the hardware I/O ports for user input, graphics timing via shift registers, and sound output. My code accurately emulated port timing quirks that were crucial to the game running correctly. Next, I built a complete testing framework for memory, I/O, and shift registers, including both unit and integration tests. This ensured emulator accuracy, especially around edge cases and hardware-specific behavior. For a development plan, I followed a structured development process, first researching hardware specs, then designing the memory and I/O systems, and finally testing and refining behavior through an iterative, test-driven approach. While development of subsystems progressed smoothly, integration revealed issues with inconsistent design patterns due to the variety of AI tools and independent development styles. I focused on standardizing interfaces and enforcing a uniform code style, which required some rework but significantly improved maintainability. Some subsystems needed refactoring to align with overall emulator architecture. Coordinating between AI-generated code and human-written glue code introduced complexity, especially when debugging interactions between memory, CPU, and I/O modules. The AI model tools I used were ChatGPT, Claude.ai, DeepSeek, and GitHub Copilot for coding, debugging, and test writing. Development was managed with VS Code, Codespaces, GitHub projects, and planning materials via Google Docs and Drive. Overall, I felt I deepened my understanding of hardware-level systems and how to represent real-world hardware in modular, low-level C code. Learn to build secure and testable emulator infrastructure, reflecting physical memory and I/O constraints. Realize the value and limits of LLMs in a software engineering context. While they can accelerate development, human critical thinking is essential for verifying correctness, avoiding subtle bugs, making architectural decisions. Practiced effective prompt engineering, learning how to phrase problems clearly to get useful and usable responses from generative models. Gained experience in remote, asynchronous development using GitHub projects and code spaces. Learned to manage roles and track tasks clearly, even with AI-generated components playing a large part in the codebase. This project reinforced how AI and humans.
Hi everyone, I'm Chongman Chen. I was mainly responsible for implementing the Intel 8080 CPU core, including the instruction execution loop. I also wrote the opcode handlers and worked to ensure that the emulator matches the correct CPU behavior and timing. Okay, I also developed unit tests and RAM testing for CPU to verify the correctness of each instructions and fix bug early. For this project, we use C with CMake and CTest for building and testing. I'd also use ChatGPT 4o to help with debugging, output generation, maintaining a prompt log, and writing test cases. My developed steps include designing the CPU struct, building the fetch, decode, execute loop, writing opcode handlers, verifying with RAM and unit tests, and optimizing dispatch and timing. Our original plan was to build a basic CPU loop, implement all opcodes in one file, write minimal unit tests, use AI to accelerate development, and run through RAM tests after finish the opcodes. But as development progressed, a few areas changed. As opcode logic grew, we refactored shell macros into ophelpers.h to avoid duplication. Our unit tests also expanded. The original ones missed some flag and timing edge cases, which only showed up during RAM tests and debugging. So we added more target tests to catch those issues early. And we delayed through RAM testing until the core opcodes were stable enough to give meaningful results. For AI-assisted development, we initially used ChatGPT 4o to generate opcode handlers and debug code. But as we review the AI output, the prompt log reveals some gaps, like incorrect cycle counts or subtle flag mistakes. We refined our prompts and review AI-generated code more carefully over time. One of the main challenges was inconsistent AI-generated code. Cycle counts, flag parity, and push-pop behavior sometimes varied. We had also found Lithuanian bugs and had to manually analyze RAM debug stumps. To address this, we improved our prompts, add target tests, enhance debug logging, and cross-check with the Intel manual. As I mentioned in previous slide, I learned a lot about the limitations of AI-generated code. In future projects, I will pay closer attention to the prompt log to maintain consistency and cross-check frequently to avoid late-stage surprises. I'd also found that unit tests are a great way to verify AI-generated code. I'd also deepened my understanding of CPU and low-level logic. Using macros help with test coverage, and starting RAM testing earlier will definitely help in future projects. Thank you.
Hi, this is Luke Rose for CS460 Capstone. My project is the Prompt Invader project. This is where we used AI for every step of the project for making a Space Invaders emulator. Super interesting project. My portion was focusing kind of on video, user input, video output, kind of command line interface items. It was very interesting using AI to kind of do all of the programming for this, interfacing, and then coordinating that between my other team members and actually making it output something. Using the AI can definitely lead you down a lot of rabbit holes and potentially pitfalls, and kind of putting the guardrails on is super interesting. And then also looking at the different models that are available currently in 2025. There's definitely ups and downs to all of them. And you have Claude, ChatGPT, DeepSeek, a number of others that you just run locally. And they all have their goods and bad. So working through all that was really interesting on this project. Take a look and see what you think.
Possible future directions for this project include Educational Toolkit. Package the emulator with visual debugging tools and detailed documentation to create a learning platform for students studying computer architecture or operating systems. AI Prompt Log Archive. Organize the AI-assisted development prompts into a chronological log to showcase the iterative process and aid future reference or research. Modular Reuse. Refactor emulator components for adaptability, allowing reuse in other retro systems like the Z80 or NES, and support for additional games built on similar hardware. Future projects. Apply the skills, patterns, and insights gained, both technical and collaborative, to future AI-assisted software development initiatives.